In this video, we're going to talk about the finite complement topology. Before we get into that though, let me remind you just in general what a topology is. So if you're given a set X, a topology on X, it's going to be a collection, fancy T, I'll just say T from now on though, of subsets of X. So I'm saying that T is some subset of the power set of X, right? It's just a bunch of subsets of X. But I can't just pick the subsets all willy-nilly. T has to satisfy the following criteria. So number one, the empty set has to be in T, and the whole set X has to be in T. So I have to always include those two subsets in a topology. Number two, if you have two things that are in T, then their intersection has to also be in T. And number three, if you have a bunch of things in T, so if, I is any index set, so typically like I is the natural numbers, we typically label things by saying U1, U2, U3, but like there's no rhyme or reason to say why we have to use natural numbers. So for any collection of subsets, for any subsets that I have in T, their union has to also be in T. So arbitrary unions of elements in T have to be in T. Let me give you some vocabulary too. If U is an element of T, we're going to say that U is open, or it's an open set. So open just means that it's in the topology T. And another way to say that is open in the set X. But again, that's all determined by just being a member of the topology. And before we go on to the finite complement topology, let me just remind you or inform you of what are topologies like useful for. It's a really abstract, weird thing that we do, a weird way to look at sets. But some of the reasons that they're useful, this list is not exhaustive, nor is it in order of importance. But one thing is that they allow us to describe what points are sort of close together without having to have an actual distance function on the set. One other thing is that continuity is born out of topology, like it's naturally described via topology. It comes from topology. And one more thing is that it allows us to classify surfaces based on some of their fundamental features. So like one example of that would be, how many holes does a surface have? And so if two surfaces are, similar in some topological way, then the properties that one surface has, you'd expect the other surface to have those same properties too. So again, mathematicians are kind of like biologists sometimes. We like to classify things and kind of put them in a box, and everything in the box has some kind of shared qualities. Now let's finally get into what is the finite complement topology. And really the rest of this video is just aimed at like how would you solve an exercise that says show this is a topology? What are the things that you need to do in general? So let's let X be an infinite set. And we're going to define T to be the following collection of subsets of X. So I'm saying take U to be a subset of X, right? It's an element of the power set. Such that though, the criteria for U to be in T is one criteria is that its complement, X minus U. I'm using that actual minus sign for the complement of a set. Some books use different things for set complement. But so the complement of U is a finite set. But then what we're also going to do is at the end, we're going to go ahead and throw the empty set into T as well. Okay. So what we're going to do is we're going to prove that T is a topology on X. Before we jump into the proof, oh, by the way, T is called the finite complement topology. Some books refer to it as the cofinite topology. So either one of those, they mean the same thing. But before we jump into the proof for this example, we're going to come back to it in a minute. I just want to give you kind of a hands-on, what would this look like in a specific instance? So I need to give you an interesting infinite set X, and let's just take the real numbers, because I'm sure if you're watching this video, you've come across the real numbers before. And I can draw you some pictures on the real line, because it doesn't require an art degree to do this. So there's my real line. And let me just give you one set. Say the interval from minus infinity to 0, union 0 to infinity. I claim that that should be an element of this collection of subsets T. And how come? Well, remember the criteria is either this set is empty, which of course U is not empty, and there's this picture right there, by the way. So the other criteria is that, well, its complement is finite. And the complement of this set is just the point that you miss, which is just the point 0. All right, so this U that I've drawn for you, that would be open in the finite complement topology because its complement just has a single point in it. It's finite. And let me consider that one again, so try to demonstrate some of the other criteria to be a topology, and going through 1, 2, and 3 from our definition before. Let's say I keep that U1, and let's say I make another set U2 that looks similar, and I've drawn it for you there. So it's the union of minus infinity to 2 with 2 to infinity. So I claim that their intersection should be in the topology as well, because if you take their intersection, well, that would just be the union of those three intervals, right, where you get a break from minus infinity to 0, from 0 to 2, and from 2 to infinity. And I claim that that's in the topology because I see that the union of those three intervals, you just miss the point 0 and the point 2. So in other words, the complement of U1 and U2, it's a finite set that has two things in it. Last thing that I want to notice is if I take the union of the blue with the green, if I take the union of the blue with the green, that gives me the whole real line back. And I know that the whole real line is going to be in the finite complement topology because the complement of R in itself is empty. And I know that the empty set is part of the topology here by definition, right? That's how we threw it over there off to the end. Okay, so now that we've got maybe a specific example of like some instances of some open sets in the finite complement topology, let's go through a proof to actually show why is it a topology. So remember, X is an infinite set, and just for convenience, I've rewritten the definition of the set T here that we're going to show is a topology on X. So remember that there are three things that we need to show, and we're just going to do them in order. And I'll keep them in white, and then I'll continue the actual proof of these things in this greenish color. So the first thing you need to show is that the empty set is in T, and that the whole set X is in T. Well, by definition, if you look up there in the yellow, the empty set is definitely in T, right? It's over there to the right-hand side. We've included it. So what we just need to justify is why should the whole set X be in T? But if you take the complement of the whole set, you just get the empty set back. And remember, that's a finite set. The empty set is the set that has 0 elements in it. So of course that's finite. So we've just verified that the first criteria for T to be a topology is true. Let's move on to the next one, which is if you took two things from the topology, I need to show you that their intersection has to also be in the topology. So let's let U1 and U2 be two things from T. Now remember, I'm trying to show you like proof techniques here in general too. And here's where you got to think about, what the hell does that mean if U1 and U2 are in T? That means that they satisfy the criteria to be in T. Either one of U1 or U2 is empty, or just that their complement is finite. And so what I'm going to say is that means X minus U1 and X minus U2 are finite sets. I'm kind of skipping over the case if one of them is, say, the empty set here, because I know the intersection of anything with the empty set is just empty. So it's kind of the non-interesting case. So let me just stick to the interesting case here. What if the complement of U1 and U2 are each finite sets? Let's think about De Morgan's laws. So this is something that you've probably come across in maybe an intro to proofs class. Remember, De Morgan's laws tells you how complements play with intersections and how they play with unions. And if I take the complement of U1 intersect U2, that's what I've written for you here. When I take the complement of that, that's the same thing as the union of the two complements. So that's X minus U1 union X minus U2. But each of these things I'm taking the union of are finite sets. And if you put two finite sets together, if you take the union of two finite sets, of course you get something back that's still finite. So that shows that's the complement of U1 and U2, the complement of U1 intersect U2, is a finite set. Thus, the intersection is an element of the finite complement topology. Last thing we got to do, if you had any collection of subsets of T, so for UI is in T for each I and some index set I, what I need to show you is that the union of all those UI is also in T. So let's start off. Let's let UI be in T for each I in the index set I. Same kind of thing. Now we need to think about, what does that mean? What is something that I could write down to start manipulating? And here is where, kind of like before, well, that just means that, again, the complement of UI is a finite set for each I. And again, I'm kind of skipping over the case that what if some of them are the empty set? Well, you don't really get a lot of new information if it's the empty set. You'd just be looking at the ones that are not empty anyway. So again, we're just going to kind of consider the case here that's, let's just look at all the ones that are non-empty. So anyway, remember the criteria to be in T is that the complement X minus UI is a finite set for each I and I. Now again, let's kind of do this De Morgan's laws trick here, right? Of course, De Morgan's laws are going to be important in something that involves unions, intersections, and complements and how they should all play together. So if I take the complement of the union of all these UI, that's the same thing as the intersection of the complements. So in other words, like do the complements first and then look at what they all have in common. And I want to emphasize that, that intersection, that consists of the elements that every single x minus ui shares, that is in all of them. But if it's in every single one of them, then that means it's in it's in x minus uj for some j. And really, the intersection of all of these x minus ui would be in each individual x minus ui. All I really care about is that it's in one of them. So let's just say it's an x minus uj for some j. And I'm just picking that off just to try to emphasize here that we just showed that the complement of the union of all these ui is contained in some finite set. Right? I know x minus uj is a finite set. Well, if you're a subset of a finite set, then guess what? You're a finite set too. So the complement of ui is finite. Hence, what we just finished is that the union of all the ui's is also in T.